Shall we go to the majestic and still mysterious theory?
Sure.
Before you explain what superstrings is about
Yes.
and its beauty, tell me what is the beauty of one single string?
Well, the idea in string theory is that elementary particles, instead of being point particles that obey quantum mechanical laws, are little loops of vibrating string that also obey quantum mechanical laws. And the beauty of that is that it describes many different things all at once. If you've got, for instance, a violin string or a piano string, they have many different modes or harmonics of vibration. If you pluck a string which is at middle C, for instance, you also see the higher harmonics. And that's responsible for the beauty of music. The reason we have symphony orchestras and not just tuning forks is that different instruments excite the higher harmonics in different amounts. The pure tone of the tuning fork sounds garish and ugly to the ear. The rich sound of a violin comes from the mixture of the different harmonics. Now, in the case of the string, you've got this one vibrating string. It has many different harmonics, and we perceive those different harmonics as different elementary particles. So, for instance, the electron, the quark, the photon, the neutrino, the graviton, all these things are different modes of vibration of a single string. And that's very beautiful and harmonious, getting the different particles from different forms of vibration of a string, just as a musician gets the richness of the tone from the harmonics of the violin string.
How small is a string? If I say small means in this case that the superstring is looks up at an atom, as an atom looks up to the entire solar system. Am I right?
Something like that. We don't understand exactly how small they are because we don't understand the theory perfectly. But roughly speaking, the proportion of the solar system to an atom is like the proportion of an atom to a string.
That's small.
That's pretty small. And it's very important that these strings obey quantum mechanical laws. Maybe I'll just take a moment at the blackboard to explain a point or two. So, classically, a point particle, as we discussed before, traces out an orbit in space, which is made a little bit fuzzy. And that fuzziness is extremely important and has a lot to do with how quantum mechanics was discovered. For instance, at the beginning of the century, when people discovered that there were atoms and there were electrons and there were atomic nuclei, they had the problem that if you've got, for instance, a proton with an electron orbiting it, and then you use Maxwell's equations, you discover that that electron should be emitting electromagnetic radiation and should spiral into the atom in an extremely short time, much faster than the twinkling of an eye. What turned out, though, is that the quantum mechanical fuzziness keeps the electron from spiraling in. The notion of spiraling in is a classical concept, and that fuzzy electron is smeared out quantum mechanically in such a way that it just can't fall in. So this cured a basic problem in the theory of electricity and gave us our modern theories of atoms, molecules, and all the microscopic things, which are based on this quantum mechanical uncertainty. In the case of gravity, there is a similar problem. If you have one body orbiting another, Einstein's theory says that gravitational radiation should be emitted. And again, you have this problem of an in-spiral. And you might think that quantum mechanical fuzziness would cure it, but in fact it doesn't. An additional source of fuzziness is needed. And you get that in string theory. In string theory, instead of a point particle, which as time evolves, traces out a loop. At each time, you've got a little string, and then at a later time, it's maybe somewhere else. And as time evolves, this fits together into a smooth surface called the world volume, or world sheet of the string. But I've kind of drawn a classical picture here. It's made fuzzy. It's hard to draw, but I won't really do so. But we've got a quantum mechanical string. So it's spread out in two different ways. One is that it's a little string instead of a point, and secondly, it's quantum mechanical. So they both have the effect of smearing out a little bit our familiar concepts and making what we know become a little bit fuzzy. And just this combination solves the problem for gravity the way the quantum mechanical fuzziness did for electricity. But it leads to a theory whose predictive power is much tighter. the arbitrariness that you've got in the standard theory is greatly reduced in the case of the string theory. And that enables you to make statements that don't have an analog in the usual context, like the fact that gravity is an inevitable consequence. Now, in talking a little bit about how particles interact, I'm not going to try to draw the quantum mechanical fuzziness. It's always there, but it would be too complicated to try to keep track of it. So we're just going to draw classical pictures. But now I want to say something that Feynman taught us, that you should think of these particles as they move along in space and time, sometimes breaking into two, and sometimes rejoining. So here, one particle broke into two at this moment, and two rejoined into one here. The overall process is that two came in from the past, and two went out to the future. So that was a scattering process, and Feynman taught us how to calculate quantum mechanical probability amplitudes for every such picture. Well, the thing about them is that everyone will agree that there were definite space-time events where something happened. One particle broke into two, or two particles joined into one. And those events are what you might call technically singularities in this graph. They're distinguished events. And standard quantum field theory needs special rules for what happens at those singularities, which is the basic limitation of its predictive power. Even after I tell you what the particles are, you don't know how they interact. Because to know how they interact, you would need to know how they're allowed to break and join. And that's a separate question. In string theory, the setup is a little bit different. Each of these particles is replaced by a little tube, which describes the history of a propagating string. And where a particle breaks into two discontinuously, a string can smoothly split apart into two strings. And then here's another one coming in. And then they go out. So now I've drawn a space-time picture of two strings coming in the past and two going out in the future. And the point of this picture is meant to be that it's all perfectly smooth. Unlike this one, which has two discrete events at which breaking or joining happened.
Mm-hmm.
So the result of that is that if you know what the string is, you also know how it interacts. You know what it's allowed to do. But if you know what the particles are, you still need a separate recipe for how it's allowed to behave. So that sort of is the germ of the fact that string theory is much more predictive than standard quantum field theory. You don't need to separately say what the objects are and how they behave. Once you've said what the objects are, how they behave is completely defined. The other thing is that technically you run into problems in standard quantum field theory when these interaction events coincide in space-time. That's where you meet infinities that people grappled with for decades. For example, Freeman Dyson was one of those who discovered the renormalization of quantum electrodynamics, where the problems for electricity were finally definitively tamed. But for gravity, that process doesn't work. That's why gravity doesn't work with standard quantum field theory. But when you go to the string, because there aren't these distinguished events, the traditional difficulties disappear. And so gravity becomes possible, and when you probe more deeply, it actually becomes necessary in the light of string theory.
If you write down an equation or a picture like that, the strings, yes. What is the beauty? Write down an equation of string theory,
yes,
which is dear to your heart. It's a kind of beauty. Explain what it's all about.
Well, the Nambu-Goto action.
You're talking about duality, for instance? Or?
We might start here with something more elementary. The Nambu-Goto action is the basic principle that determines how these strings move in space-time. And it's a beautiful equation that also governs the behavior of a soap bubble in ordinary space. So if you've ever seen the oscillations of a soap bubble, and you've ever noticed that they can take curious and graceful shapes, that's one manifestation of what this equation does. But its other manifestation is that it describes what the strings are, but it therefore also describes at the same time how they're allowed to behave, what the interactions are, how one string can break into two, how strings can scatter, what reactions can occur, how atoms can form.
It's the most complete.
Well, it's not the most complete, but it does a lot.
Yeah.
And in standard quantum field theory, that means in pre-string physics, it has no analog. Over here, you need to write bits and pieces. You can write a very nice piece that goes back sort of to Euler, Lagrange, and Newton in different aspects. And its analog, which many who've studied physics would meet as undergraduates probably. Looks like that. And it's fairly close analog of the Nambu-Goto formula.
Mm-hmm.
But it only describes a piece of the picture. And there's the rest of the truth, which is where the particles are interacting or breaking or joining or whatever they're doing. Where things are happening rather than just particles propagating freely, you need additional laws, which can't be written down neatly in this form. It takes another language completely. So in going to string theory, you replace this one. This one sort of describes a rubber band. Well, analogy is a little bit misleading. This one describes the soap bubble in the sense that this one describes something of lower dimension. But when we go from here to here, well, just mathematically, in some ways it's richer, but in some ways it's quite similar. But the physics that it describes is much more harmonious. Because a formula like this one can never give a complete account of the particles.
Mm-hmm.
You need separate rules for how they behave, how they interact, what they're allowed to do. This sort of just says what they are. But this formula says what the strings are and also how they behave. And people dreamed for a long time in physics to have something like that, where you'd automatically know the interactions once you knew what the particles were. You could say that in gravity, Einstein offered that for the gravitational field. But in the rest of physics, that's generally been out of reach. Bits and pieces of it are achieved. Something like that is achieved for the W and Z bosons on the electromagnetic field in the standard model of particle physics. But for the rest of the particles, like the neutrino or the electron, you really have got to go to the string picture before you're able to say that knowing what it is, you also know what it can do.
Yeah, in this formula you see what it is and you see what it can do.
That's right.
It's not a standstill, it's the movement of the universe, so to say.
Yeah, it
Is
describes...
it too poetic, or...?
Well, it's not too poetic, but it's not exactly the phrase I would use either.
Huh?
What I'd say, it's of course hard to convey it with perfect accuracy, but what I would try to say is that in the string case, once you say what the strings are, what strings you're trying to describe, then their behavior is uniquely determined. Whereas for electrons, you sort of dial the knobs. You can say what's the mass of the electron, what's its electric charge, and so on. And the standard quantum field theories would still make sense for different values of those numbers. In the way I've explained it so far, the way I've said it is that if you know what the string is, then you also know what it does. And that's sort of because this picture here is smooth, while this other one has those interaction events where breaking and joining happened. But that's kind of not a complete explanation. In the particle side, you've got quite a lot of freedom in saying what the particles are allowed to be. In the string side, it's severely restricted what kind of strings you can introduce. That's a long story that took a lot of work in the 70s, because finding that there are any possibilities for relativistic strings was extremely difficult and occupied literally dozens of papers. So people by the mid-80s had distilled it to the fact that there seemed to be 5 string theories that made sense. There were 5 candidates for what kind of string you could have. They differed by very general properties. For instance, in some theories, in some cases the string was an insulator. In other cases the strings were superconductors. In some cases the strings were closed loops like I drew on the blackboard. And in one of the 5 theories the strings were allowed to have endpoints, like pieces of string instead of closed loops. But anyway, when all is said and done, when you put in all the constraints of relativistic quantum mechanics, there were 5 kinds of strings you could do. So there seemed to be 5 candidates for how you could describe nature in this new framework. There was a period in the early 80s when it seemed that there was this very wonderful new framework for physics. There were 3 candidates, 2 hadn't yet been discovered. In this new framework, gravity was inevitable, while in the pre-string framework it was actually impossible. And that, of course, was very attractive and exciting. But on the other hand, you could also point to things that were wrong. These 3 theories were unified theories of gravity, quantum mechanics, and matter. But some aspects of the matter were wrong. What bothered me the most in those days was that you could argue in general that in any of those 3 theories, the weak interactions would have to conserve parity, which means that nature would look the same if you looked in a mirror. But we've known since the 50s that although nature almost looks the same if you look in the mirror, if you look very closely at the details of radioactive decays of certain atoms, you see that actually nature isn't symmetrical between left and right. If you take a movie and then you put the film in backwards and project it, most things in everyday life would look fine, but certain experiments in elementary particle physics and nuclear physics actually wouldn't make sense if the film was played backwards. Mm-hmm. Yet it seemed that you could prove in string theory that the theory would have to be symmetrical between left and right, at least for the realm of the standard experiments. That was wrong. That was a really important contradiction, I thought, between string theory and nature. And it motivated a lot of work that I and eventually others did in that period. In 1983, Alvarez Gomez and I did a calculation involving gravitational anomalies that made very precise why the weak interactions would have to be symmetrical between left and right. And then in 1984, there was the breakthrough that Green and Schwartz made, where they got a new insight about the anomaly cancellation. And suddenly the idea that the weak interactions had to be symmetric between left and right was out the window. But then a lot of other things happened. So the weak interactions could break the symmetry, but then the models of elementary particle physics became a lot more realistic in very short order, especially with the discovery of the other two string theories, the heterotic strings. So this, of course, made a tremendous impression on me, because if the theory was wrong, the question you asked, well, how can you avoid left-right symmetry of the theory, might not have had an answer. And even if you could have conjured up some mathematical answer or not, nothing good would have necessarily come out of it. The fact that when you solve this problem, so many other things popped into place is the kind of thing which, in my judgment, doesn't happen if you're on the wrong track overall. So, since then, I personally haven't had doubts that it must be on the right track. You know, how many more layers we've got to peel away before we understand it is another story.
In what direction do you
I
think,
don't have,
if you say it will completely change our way of thinking about nature and the laws of nature?
Well, you see, somehow space and time will only be approximations. I don't know exactly how, but very, very roughly, the classical idea of position and velocity of a particle is an approximation in quantum mechanics that you get when you can treat certain operators as if they commute. If you don't care which of two things is done first, then you can talk about the classical ideas. But if you pay attention to what's first and what's last, then you're in this quantum mechanical world where everything is much stranger. Now, in the framework of physics that we have up to now, position and velocity have been confounded, but space and time still are perfectly sharp. But it's very clear for a lot of reasons that in the future, the concepts of space and time are going to be fuzzed up. That there will be something new that we've got that's more basic than space and time as we know them. And space and time will be approximations that will make sense when the lengths and times involved are big. When the lengths and times involved are small, they won't make sense. That's why the very notion of time will break down near the Big Bang. If you want to understand the Big Bang, or black holes, or the structure of elementary particles, there's some deeper level about what space and time really are, which is what string theorists are grappling towards. The laws of nature, as they've been uncovered in the last few centuries, and especially as they've been uncovered in the last century, are very surprising. They're very subtle in the concepts that physicists have needed, and many of the details are surprising. We've mentioned some of them, the curvature of space-time, others that are equally surprising, like antimatter, the fact that every particle has a similar but opposite antiparticle, and they can annihilate when they meet. Or conversely, they can be created from pure energy. There are lots and lots of surprising things. Here, in that case, I'm mentioning a surprising phenomenon. But the concepts by which the human mind explains or predicts them are also, in many cases, very surprising, very different from what you might notice just naively in everyday life in looking at things around you. They've got a great beauty, which is a little hard to describe, maybe, if one hasn't experienced it. It's an aesthetic beauty The laws as we know them are very beautiful mathematically. They involve very interesting and subtle concepts.
Yeah, what do you mean by subtle?
Subtle? Well, it's very delicate. You see, if I gave you the naive idea, which is still on the blackboard, replace a definite orbit of a point particle by something fuzzy, you could think about it 1,000 people locked in a room for 1,000 years. And you might never come up with something as crazy as the actual answer, which involves quantum mechanical Hilbert spaces, operators that don't commute, wave functions that obey strange equations and have peculiar physical interpretations. So it's a rich story, and it all hangs together beautifully. And resolves many contradictions, or apparent contradictions in nature, that at first sight look just as strange as the question, what was there before the beginning? So lots of things that prove to have their explanations in strange mathematical structures that are relevant to nature seem paradoxical, just like some of the paradoxes about the beginning of time. So I think perhaps some viewers of this program might be accustomed to thinking about the beauty of music, for instance. But the beauty of science, and I might say also the beauty of pure mathematics, are very different, but they're just as real and vivid to those who experience them as the beauty of music. It's not just that in the course of time, physicists learned to write more and more accurate equations. In writing more and more accurate equations, physicists learned that the more and more accurate equations are based on new, subtle, and surprising concepts that fit together just right, resolve all the contradictions, do everything they have to do, whether it's going back to Newton's laws in the regime where Newton was able to study nature, or reproducing atomic behavior in certain other regimes. It fits together perfectly in ways that are really extremely surprising. And of course, the greatest thing about it is that it works.
Yeah.
It not just fits together logically, but it describes the world we live in. The best equations and the best theories we've got, as I've mentioned, are really quantum mechanics and general relativity. And the best theories are tested in so many different ways and apply so nicely to so many different phenomena that they really have remarkable power in describing nature. But one thing I'm trying to convey is that the thrill is not just from the power of being able to describe many things, but the combination of the beauty of the theory, beauty or harmony of the theory, and its power in application to the real world. That combination gives a thrill that I think neither ingredient would fully give separately.